Hey, really quick before this episode gets started, I am pleased to announce the new and improved Tech Bytes website, now with email newsletters. Check it out at techbytespodcast.net and consider subscribing. That's all. On with the episode. Right now, you're listening to this episode on something that contains a computer chip. Your phone, your laptop, your tablet, your smart speaker, your car's infotainment system, maybe even your earbuds. That little chip, that tiny little piece of silicon, is the most complicated thing humans have ever manufactured. I don't say that lightly. This is a process that quite literally makes building a skyscraper look like Legos. It requires temperatures that are hotter than lava, the light that doesn't technically exist in nature, and machines that cost more than a commercial airplane. Yet very few people understand how it works. We just know that these chips are in everything, that there have been several shortages of them, and that people like to argue about them on the news. Today, we're going to fix that. Welcome to Tech Bytes, where technology is made simpler for consumers. Today, we're going to look at how a computer chip actually gets made from raw sand to the thing running in your phone. No engineering degree required, just some curiosity. Let's get into it. Let's start from the very beginning. Computer chips are made from silicon, and silicon comes from sand. Now, not beach sand. You can't just scoop up sand at the shore and start making processors. But silicon is one of the most common elements on Earth. It's everywhere. It's in rocks and soil. It's the second most abundant element in Earth's crust after, well, oxygen. The reason silicon is useful for chips is that it's what's called a semiconductor. A semiconductor literally means that it is halfway between a conductor and an insulator. A conductor, like copper wire, lets electricity flow freely. An insulator, like rubber, blocks it. Silicon sits in the middle. And it's that magic where you can control when it conducts and when it doesn't. That on-off behavior is the foundation of all computers. Every app, every photo, every video call. At the bottom of it all, it's just a bunch of tiny switches turning on and off. Before you can do anything with the silicon, however, you need to get it incredibly pure, like 99.9 with 99% pure. To put that in perspective, if you had a swimming pool full of silicon, your total impurities would be about a teaspoon. To get there, raw silicon goes through this process where it's melted down at over 2,500 degrees Fahrenheit, purified, and then grown into a single crystal, which is essentially just a giant cylinder about the size of a telephone pole segment called an ingot. This ingot gets sliced into thin, round discs called wafers. If you've ever seen photos from a chip factory, those shiny, perfectly round discs are what you're looking at. Each wafer will eventually become hundreds of individual chips, and this is where the real engineering begins. So now we have a wafer, a thin, polished disc of ultra pure silicon, but we need to make some circuits on it. And when I say circuits, I don't mean like wire you can see from a tinker's kit. I mean like circuits that are so small a human hair is 10,000 times wider. Well, how do you build something that small? You can't use standard tools, and you certainly can't just use a laser pointer. This is where you get a process called photolithography. And this is where chip manufacturing goes from impressive to straight up mind blowing. Here's the basic idea. Your wafer gets coated in a material called photoresist. Think of it like a very thin coat of paint that reacts to light. Then, a pattern is projected onto this wafer using an extremely precise beam of light. Wherever the light hits, it changes the photoresist. Then, you wash away the parts that were changed or the parts that weren't, depending on your process, and you're left with a pattern on the surface. Then, you can etch the exposed silicon, deposit new materials, and build up layers. It's basically the same process as developing photographs in a darkroom, just on an insanely small scale. When I say insanely small scale, this is where it goes from mind blowing to truly insane. The features of an individual part of a modern chip are measured in nanometers. Your current cutting edge is around 2 to 3 nanometers. Now, a nanometer is a billionth of a meter. And for reference, an atom is roughly a third of a nanometer across. We are literally building structures that are single digit atoms wide. The problem is that the light used to print these patterns has been a wavelength that was actually bigger than the features being printed. Deep ultraviolet light has a wavelength of around 193 nanometers. How do you print a 2 nanometer feature with a 193 nanometer beam of light? It's like trying to paint a straight line with a roller brush the size of your house. You just can't do it. The industry solved this with a technology called EUV, or extreme ultraviolet lithography. EUV has a wavelength of just 13.5 nanometers. To generate it, a machine fires a high-powered laser at tiny droplets of molten tin 50,000 times per second, and each droplet explodes into a plasma that emits EUV light. That light then bounces off a series of the most perfectly polished mirrors ever created and is focused onto the wafer. It sounds like science fiction, and honestly, sometimes it feels like it. These EUV machines are made by one company in the entire world, a Dutch company called ASML. Each machine costs somewhere in the neighborhood of $200 million, weighs more than an airplane, and takes multiple 747s with 40 shipping containers just to deliver one of them. Every advanced chip being made totally depends on them. And remember, these companies that use the machines, they aren't buying just one. They're buying an entire manufacturing facility's worth of them. So photolithography is how you print the pattern. But a chip isn't just one pattern. It's many, many layers that have been printed, etched, and built up separately, stacked on top of each other. Think of it like building a city. You don't just put in streets. You put in streets. Then you put in the plumbing underneath. Then the buildings and the wiring and the floors and so on. A modern processor can have over 100 layers. Each layer serves a purpose. At the very bottom, you've got the transistors. These are the very tiny on-off switches that I kind of talked about earlier. A modern chip from Apple or AMD has billions of them. Not millions, billions. The M series chip in a MacBook has around 20 billion transistors. Your phone probably has somewhere in that range too. Above the transistors are layers of wiring, incredibly thin metal connectors, usually copper, that link the transistors together. These wiring layers are like the road network of a chip. The transistors are the buildings, and the metal layers are the highways and side streets connecting them. Between each layer are insulating materials to keep signals from interfering with each other, because when you've got billions of switches flipping billions of times per second in a space the size of your thumbnail, crosstalk becomes a real problem. The whole process from blank wafer to finished chip takes about 3 to 4 months. The wafer might go through the lithography machine dozens of times, once for each layer. Between each stop, there are cleaning processes, inspections, chemical treatments, and quality checks. One speck of dust in the wrong place could ruin a chip, which is why chip factories, which are nicknamed fabs, are the cleanest places on earth. The air in a fab is thousands of times cleaner than a hospital operating room. Workers wear full bodysuits called the bunny suits, not because they're cute, but because a single flake of skin or strand of human hair can destroy millions of dollars worth of product. That was a lot. Let's zoom out a little bit and talk about the industry, because this is where it becomes more interesting and gets relevant to you. There are only a handful of companies in the world that manufacture these chips. By far, the biggest is TSMC, or Taiwan Semiconductor Manufacturing Company. TSMC makes chips for Apple, AMD, Nvidia, Qualcomm, and dozens of other companies. When you hear about the new chip in the iPhone, Apple designed it, but TSMC built it. This is an important distinction. Many of the companies whose names you know, like Apple, Nvidia, Qualcomm, and Broadcom, design the chips, but they don't manufacture them. They're called fabless companies. They send their designs to TSMC or another foundry, and they get finished chips back. Samsung in South Korea also manufactures advanced chips, and Intel has been both a designer and manufacturer for decades and is heavily invested in building new fabs in the US. The concentration of manufacturing in Taiwan has made a lot of governments nervous. Taiwan produces the vast majority of the world's most advanced chips. If anything disrupted that, such as a natural disaster or a geopolitical conflict, the entire global technology supply chain would grind to a halt. Phones, cars, data centers, medical devices, military systems, all of it depends on chips coming out of a handful of buildings on a tiny island in the Pacific. That's why the United States passed the CHIPS Act back in 2022, committing tens of billions of dollars to building new chip factories on American soil. Europe and Japan are doing similar things as well. It's not just about the technology, it's about economic security and national security. Then there's ASML, that Dutch company that I mentioned earlier, which makes the EUV machines. ASML is the only company in the world that makes them. That single point of dependency means that the export controls on ASML equipment have become a major tool of international policy. Both the United States and the Netherlands have restricted the sale of advanced ASML machines to certain countries. When you hear about chip export controls on the news, this is often what they're talking about, not the chips themselves, but the machines that make them. Now, why does this matter if you're not an engineer or a politician? Well, there are a few reasons. First, it affects the price and availability of everything you buy. The chip shortage during the pandemic made that painfully clear. Car dealerships had empty lots because modern cars need dozens of chips and the fabs couldn't keep up. Game consoles were impossible to find. Appliance deliveries were delayed. The entire global economy learned the hard way that chips aren't optional anymore. They're fundamental, like electricity and steel. Second, the pace of progress in chips is what drives the pace of progress in everything else. The reason your phone today is more powerful than the computers that landed astronauts on the moon in the 1960s isn't because of one breakthrough. It's because the chip industry has been relentlessly making these transistors smaller and smaller and packing more of them onto each chip for 60 years. That trend is what made smartphones possible, what made streaming video possible, and what's making AI possible right now. And third, understanding where the chips come from helps you understand the news when you hear about tensions involving Taiwan or export controls or a new factory being built in Arizona. Now you know what is actually at stake. It's not theoretical policy, it's the supply chain that your daily life relies on. Hopefully, now you understand a little bit more about how the chips in your computer or phone are made. I'm going to leave you with one image. Take out your phone and look at it. Somewhere inside that device is a chip that's about the size of your fingernail. On that chip, there are more transistors than there are stars in the Milky Way galaxy. Each one was printed with exploding tin and impossible mirrors in one of the cleanest rooms on Earth on an island in the Pacific using a machine that took decades to invent and costs more than most skyscrapers. And it all started with sand. That's going to do it for this episode. If you found it interesting, share it with someone who might not know how their phone was actually made. I think they'd be surprised. Thanks for listening to Tech Bites, and I'll see you in the next one. Thank you.